Hello everyone, my name is Pedro. I'm the ESR6 from the Team Up 5G project. And today we are going to talk a little bit more about simulating a network assistance scenario using UAVs. In summary, I'll give you some introduction about the subject, of course, application and scenarios. I'm going to present some applications and scenarios. I'll talk a little bit about the UAV-assisted network paradigm. I'll also give some a simulation scenario, a simulation environment for you to understand. Then after simulate these scenarios and environment, I will also show some results that we can obtain after simulation. And finally, a conclusion. Firstly, I have to say that today we have a high demand for computing and network resources in a short period of time. We know that today we have a high demand for computing and network resources in a short period of time. And according to Cisco, the mobile and wireless network will be carrying about 77 exabytes per month at the end of 2022. And we also know that the need for resources moves according to the characteristics of the service, application, or the event. We can also say that today we have improved devices such as smartphones that's coming more and more advanced with new technologies such as AI, for example. And besides of that, we also have multiple services, growing smart city solutions, and all of this brings a new and challenging requirements. On the other hand, we have an ultra-dense network. This means that we have a lot of devices that needs to be connected and also needs to transmit its data. And we might have some problems such as line of sight link limitations and lack of adequate infrastructure in urban or remote areas. So here we have a picture that shows most of the main scenarios and applications. And these applications are usually on-demand application and services. Some of those are in hard-to-reach areas. And another kind of events are the flash crowd events that happens when we have an increased data rate in a short time range. And this example, we have some immersion to specific environment, such as in stadiums and concerts. We have public safety scenarios, transportation management system, data collection in large areas, such as what works in IoT. We have real-time surveillance and monitoring scenarios, which can support which gives support to first responders and victim detection. And we also have the post-disaster recovery scenario. So the UAV assisted network, what it is, what it means. So some of the key aspects in the UAV assistance paradigm, according to Alzarani, by 2020, are these ones listed here: UAV data gathering, UAV monitoring, UAV computing, disaster management, cellular communications. And we also have some other ones: UAV routing, UAV IT networks, UAV security communication, UAV and unmanned ground vehicles coordination, and so on. Under these aspects, we can provide different kind of solutions and give support to different kind of applications. So what happens in a UAV assisted network is that we have most of users being attended, or fewer users with poor connection or service, working but possibly congested BSS. That means the ground infrastructure might be damaged or might be overloaded. And application and services, we have cellular communications, monitoring, surveillance, police patrolling, edge computing, network congestion relief. Most of these applications can be assisted by using UAVs. So our simulation scenario will be, we're going to deploy static user equipment randomly distributed over the area, one macrocell, and a set of UAVs that will be working as small cells. And basically, the simulation environment, we're going to use the ANA3 simulator, where this will be the main parameters. We're going to start by, we're going to simulate a scenario with 30 user equipments, one macrocell, and the number of UAVs we can vary and see how does it impact on the scenario. So basically, our program, our simulation, we have to initialize the nodes and its initial mobility. Like we have to load all the kind of nodes that we are aiming to use, and how many of each one. We also have to define separately in a different file. It's actually a Python script, the UAV deployment script. That means how the UAV will be deployed. In our case, we are going to execute only a random deployment of such UAVs. And okay, and after that, we have to configure the LTE components, as we are going to use LTE for the simulation. It's also important to set up the callback functions, as some of those will be important to generate the results that we are going to analyze. So let's do it. So let's get started with the ANS3 simulation script, the main script. And here we have some inputs that can be defined by the user when calling the simulation script. In our case, we're going to define the time of simulation, the number of user equipment, the number of PSs or macrocells, the number of UAVs. Basically this. After that, we have to define the mobility of the users. In our case, we are using a random mobility. That means, which means that we're placing the users in a random way over the area in a minimal altitude of 1 meter 0.5. It's because NF3 requires that the altitude of every node it cannot be 0. So we replace this value that's more or less can be considered as the average height of each user. And as I said, we put the random deployment. So basically define so what I have so far is that we have the mobility, the user equipment mobility defined through this function. So here we actually define the positions that the position of the users in this function, that will be a random position, the number of users, and the altitude of each user. We then create the user node itself, that it's a node container in ENA3. After that, we're gonna create a mobility helper object that will help us to define a constant position model, mobility model. That means that the users will be static, and we install it on the nodes that has been created, on the node that have been created in here. So install it. And then we do a similar step to the macro cell. We create the macro cell and with the number of macro cells that we want. In our case, is only one, but in this case, the position are loaded this way. This function do a similar way, but in a more advanced way. In the case of the BS mobility, the BS position, the macro cell position, we define here the actual position of each BSs. If you want to add more BSs, you must add the other positions. Like if you have, in our case, we have only one, so we just add only one position. If you want 2 or 3 BSs, you have to add the respective position of such BSs. Okay. After set the positions of the BSs, we set the mobility of each BS. That is also a constant mobility model. That means that BSs are static. It means it's and then the last node that we have to configure are the UV nodes. So for this one, we generate its position using a Python script that runs inside this function in here. And this is important because every time that the NF3 detects that a user equipment is poorly assisted, it will count the number of poorly assisted user equipment and then generate positions over the area where these poorly assisted user equipments are. So it basically loads a new set of positions with the same number of UEVs every certain period of time. So in here we are actually creating the nodes, the NF3 nodes. We are setting which mobility is this, and in this case we say that the mobility of the UEVs are a constant mobility model. It means that the UEVs can move over the area with a certain speed that is defined in another file. And then we load the positions in this mobility model, and we also install it on the nodes itself. Okay. And then, as we defined in our second step is configuring the LTE components. So in here we are basically configuring them. These are the basic configuration when using the LTE. I will not explain in details this part, but we are basically defining all the LTE architecture components through these steps here. I will also provide a link where you can check more details about it. Then a very interesting part of the code is the energy module, where we are installing the energy module into the UAVs, and then we can then analyze how much energy each UAV is spent during the simulation, and maybe in the future provide a solution that it's more aware of how much energy each UAV is spending. So energy aware solution, okay. And yes, we are installing the energy stack on the UAV node. Okay. So here we are defining the another. So here we define the other LTE parameters like carrier aggregation, number of component carriers, what else? The download bandwidth, upload bandwidth, the transmission power of each node, um, the path loss model, the handover algorithm that we are going to use in it, and then we jump to the IP stack, where we define the IP of each node. So after define the IP stack, we define the application. In our case, we are going to use a CBR, a constant bit rate application, with 1 megabits per second. It means that each user equipment will require at least 1 megabit per second. It's the minimum requirement. And then we are basically configuring the application in here, when it will be starting and when it will be finishing. We are also installing it on the remote host that is in the LTE architecture. Yes, and it's basically this. It's important for collecting the data, so we have to define it. This is for a control, a log purpose, to see what's wrong. What else? And here, and finally here, we need to set up the callback functions that will be important to generate our logs. Okay. So this callback here, it's important for us to create a energy depleted file where the energy of each UAV will be written. What else is important in this part is when the connection are established between a user equipment and a inode V that could be both a macro cell or a small cell, in this case a macro cell or a UAV. This function is also important, this two here, because this callback it's actually a scheduler. We are actually scheduling a function to start after 1 second and repeat every 1 second, and we basically calculate our QoS parameters in this function in here, that you can see that it's in here. I can show more detail later. The other function is it's save node position that is important to keep the position, keep a file with the position of every node, including the BSs, including the user equipment, and also the UAVs, of course. So let's jump to the QoS monitor function. The QoS monitor function takes as argument a flow monitor object, that in this object is inside this object we can check all the QoS parameters such as jitter, throughput, the number of lost packages, the number of transmitted packages, the number of received packages. We can also calculate the PDR, the PLR, the delay, throughput, jitter. Yes, and that's how the QoS parameters are evaluated. And you can check later the details of this function. And it's basically this. The other function that I want to show you is a function. Why this is important? As I told you, this function will be called will be called every time that we have in, we will call it in here, and yes, in here. This part will be executed only if you have a more than zero, one or more user equipment that is being poorly assisted. And what this function does is it every time that it's executed, it reloads, it's rerun our Python script. This Python script is the one that generate the UAV's position that we are using to generate the UAV position. It's executed in this function here. This function here, it's inside the main. That's the first time we call it. But after that, we call it in a different way because it's a matter of simplicity. So we call it through this other function that is basically the same, but it returns a different value, a different type of variable, in this case a string. And inside this string, we're gonna have the positions generated by this script. So let's check out how this script works. So here we have this script. We can execute it as I did previously. So how we execute it? We have to put as parameters the positions of the user equipment in here with this argument, the altitude of the UAVs and the number of the UAVs that we want. And once we run it, we're going to have this first part before the hashtag is how much time this script took to run and give the result. And the second part after the hashtag, it's the position itself. You can see that we have the X, the Y, and the altitude here. Okay, and we actually have 12. In this case, we have 12 positions. So it's basically this, and the function that executes this, a Python script, is here. This function that runs a command, this command here. So it's basically this. Don't worry about read all these lines for now. I provide the link for this code, and you're gonna see something similar to this.